Now we are starting the last session of today. This session is designed for 4 presentations. The abstracts received are evaluated by the scientific committee, and these 4 abstracts are accepted to be presented here, and the others are poster. Probably you have seen in the poster session. You have the program over there.
Yeah.
Now, let me introduce you our first speaker. Very small. Anke Grunwald.
Perfect.
And she's the managing director of Berlin Wind GmbH.
Yeah,
GmbH. And she's the founder also of the Berlin Wind GmbH since November 2009. Before, she had been for 5 years with Deutsche Windguard Dynamics GmbH as marketing and sales engineer and assistant manager director of the measurement department. Anke started her career in the wind energy industry working for the German Wind Energy Association, where she managed and edited the annual publication Wind Energy Market Survey. So she will make a presentation to us on boost wind turbine yield and life expectancy through rotor blade angle correction. While she's getting ready, maybe I should introduce myself. I'm from Marmara University and head of the energy section, and trying to promote 100% renewable energy in Turkey. We know that the first solution is always energy and use efficiency. Then the rest we talk about as symphony of renewables. So if we don't do this, we cannot reduce the size of the problem. And as we know, the character of renewable energy compared with conventional energy technologies, renewable energy is a high entropy resource. It's everywhere, and wherever it is, you can concentrate and produce whatever you need. The technologies are available, resources everywhere. But we need to manage this traffic. That's why we need smart grids and storage to make renewable energy independent from fossil fuels. So that's what we are trying to promote as Renewable Energy Association of Turkey, Eurosolar Turkey. I have also distributed you the next activity we have in May, the 5th 100% renewable energy conference in Istanbul. You are welcome to send abstracts and be a part of these efforts. Thank you very much. Now the word is yours, Anke. You have about, how many minutes?
I need 20.
20, okay. You use 20 minutes.
I can try to
we already
fast.
Don't have one speaker yet. Let's see. The rest time we save, we use for discussions with the audience. Please, time is yours.
Okay, thank you. Welcome, ladies and gentlemen, to the last session, and thank you for.
Microphone is open?
I think it's on, is it? Do I have to be closer? Yeah.
Translators are okay, yes? Okay, good, perfect.
Okay, yeah. I want to just start with a short introduction of Berlin Wind, what we are doing. So it was already mentioned, we were founded in 2009. We are part of a bigger holding, Corporate Energies Group, that is also located in Berlin, Germany. But we work worldwide. We also have other strategic partners we work with. We are independent experts with a long experience in the wind energy industry. So some of us have up to 20 years experience in this industry. We are also an active member of the German Wind Energy Association. We are in their expert advisory board of that association. And also we are part of a work group for a German standard concerning the vibrations of wind turbines. what we offer is mostly we focus on the optimization of the performance of the wind turbines, and what we do most are blade angle measurements and rotor imbalance measurements. And we have measured so far for more than 1,000 turbines, and of all different types and different manufacturers. And beside that, we also do, for instance, load measurement campaigns, vibration measurement campaigns. We also do consulting, for instance, finding root causes and optimize performance of wind turbines. We heavily focus on R&D in our high precision measurement procedures, and we have our own hardware and software developed for these blade angle and rotor imbalance measurements. I'll just jump this and go right into the impact of blade angle deviation on the power curve of wind turbines. Please note this is a schematic diagram. The green graph represents the design power curve, so the optimum power curve you want to have. If you have any deviation of the blade angles, we will have a deviation of that, and it will be a lower power curve. If you have a misalignment towards feather, then we will have always a lower power output till the rated wind speed. If you have a misalignment towards stall, then we might have a little bit of higher power output for the low wind classes, but that comes at a high price. For the higher wind speeds, we do have significantly lower power output, and in addition, we will also have significantly increased vibrations and loads. Here, it shows you an estimation, how to estimate the level of production loss you will have by blade angle deviation. We often ask it like that. How much will that be? So we have used two approaches. One is an analytical one, the red dotted line you see here. We used, therefore, wind tunnel profile data, and we came up with 10% power output reduction per 1 degree of misalignment. The second approach, we used operating data. We looked at a wind farm with 10 wind turbines, where we measured the absolute blade angle deviation. So this is this graph. And we compared the production data with these affected turbines with a reference turbine there. And this is how we came up with this value, that we have about 7% loss of annual production per 1 degree blade angle misalignment. But because there are other factors you have to count in, for instance, how many blades will be misaligned and in which direction, we have drawn a range around that. But even if we are at the lower limit of this range, we still have a quite impressive yield reduction from blade angle deviation. Besides that yield reduction, we will also have an increase of vibration amplitudes, fatigue loads, lifetime consumption, and operational expenses from damages and coming also from downtime. Here you see one example of one turbine with a really big blade angle deviation of about, oops, that always meant like that, 6 degrees, which is huge. But it shows you, here we had also severe damages just after 1 year of the foundation of the wind turbine. And what you see here are some cracks. What we did there, we adjusted the blade angles in 2 steps. First to the kind of critical limit value of about 0.5 degrees, around that. Then we did the final adjustment, and then we also did mass imbalance correction. So the red columns are the initial state of the vibrations in axial, lateral, and torsional direction of the wind turbine. They are normalized here. And we see we have a huge reduction by adjusting the blade angles. And even with the fine adjustment of just about 0.5 degrees, we still have a noticeable decrease of the vibrations. And then in the final stage, it looks tiny here, but it's still a 50% reduction of the vibration amplitudes due to the mass imbalance correction we did. So I've been talking a lot about blade angle deviation, so what do I mean? I'm talking about the absolute blade angle deviation. You see here, we have the green dotted line is the design blade angle, where we have the optimum production. And if we have a deviation of that, we call it absolute blade angle deviation. And this is mainly responsible for the yield loss. A relative blade angle deviation, there we have a deviation between all the individual blades, which mostly result into increase of vibrations. But any deviation will have an increase in the asymmetric forces and thus increase the operational loads. And this is also the reason why we have critical limit values, because an increase of these operational loads, they mean a threat to the safety of the turbine. And that's why we have, we have these critical limit values in the design standards. For instance, we have one in the GL guideline, Germanische Lloyd. We have plus minus 0.3 degrees. And from that, we also derive the relative, or the limit for the relative blade angle deviation, that would then be 0.6 degrees. First, that sounds really tiny, small values. But if we look at the huge rotors with 80 meters diameter and more, the measurements we have done, we have seen they're really sensitive to small adjustments or deviations of the blade angles. If we correct the blade angle, or one blade, by 0.2 degrees, we will see a noticeable change in the vibrations. So now we'll show you some statistics of our measurement we did. Here I show you the result of nearly 300 measured turbines, where we had sometimes suspicions, sometimes not, that they are affected by blade angle deviation. We measured the absolute blade angle deviation and came up with these results, looking at the individual blades, that about 20% of them are within the tolerance for absolute blade angle deviation. That's the nice green part here. And while the rest will exceed that critical limit value. And we have about a third where we have a misalignment towards feather. And here we have about half of them where we have a misalignment above the tolerance towards stall. That means with this part we also have, besides the power loss, also vibration issues. What we found there, the mean was not really zero. It was more towards stall. It was minus 0.34 degrees. And we quite have a huge standard deviation of about 2 degrees. So as statistic values here. And we do have some really worst cases where we have about 10 degrees deviation. So it's a serious issue. The next slide shows you the same, it's based on the same measurements, but now we look just at the rotors. So 3 blades belonging to 1 rotor. That means we have here even a smaller share of rotors where the blade angles are within the critical limit. And that's just 7% here. And the rest we have, here both the relative and the absolute blade angle deviation will be above the critical limit. Here we have the relative blade angles, they're tolerable, but the collective blade angle means the absolute blade angle will be still bigger than the critical limit value, bigger than 0.2 degrees deviation. Meaning that we also have yield loss there, and even though we have less problems with vibrations. Now my last pie chart. We took the data of the wind turbines where we measured the absolute blade angles, and we combined them with some data of an earlier measurement where we measured 240 turbines, but not the absolute blade angles. What we measured there was just the relative blade angle deviation and the mass imbalance. But for these 240 wind turbines, we didn't have any known issues with the blade angles or with the mass imbalance. So we combined these two in order to figure out what to expect if you look at a wind farm. And what we found was that about a fourth share of these turbines would be within the limits for blade angle deviation and also for mass imbalance. But the bigger part, 3/4, would be exceeding at least one of these critical limit values. So it is a big issue, and we will have to deal with the consequences of damages, standstill, loss of energy production, noise issues as well, especially from blade angle deviation. And as a side note, if you want to calculate the mass imbalance properly, you have to adjust the blade angles before, otherwise you will have false results. So I will show you here a procedure, or that's our proven procedure for measuring the blade angles and adjusting them and validating the result. So we record a series of pictures for each blade. So we have a statistic safety. Then we evaluate all these pictures using our software. Then we check, do we have a blade angle deviation or not? If we have one, we do a vibration measurement before adjustment and one after the adjustment. And that will help us to prove that the vibration, that we turned the blades in the right direction, and also that we lowered the vibration. The other advantage is that when I measure the blade angles optically, often I measure just at a certain radius, maybe at one radius, maybe at two radius along the long blade. But all the blades have a certain blade twist, and we have tolerances there. And if we do a vibration measurement that takes into account kind of the whole, the loads, everything along the whole blade, so we are able to still adjust the blade angles also in order to minimize the vibrations. And while it's also possible offshore that we use a laser-based system, and we can, of course, use the vibration measurement in the last step to check on the mass imbalance as well. Yeah, why go through all this hassle with this measurement, what I described before? What I described before, maybe to give you an idea, would take less than a day on site at a turbine. So if you maybe just do pictures and later analyze them, then you can do several turbines a day, just taking pictures and then coming back for adjustment. So why go through all this? Why not just look at the 0-degree marks of the blades? Because we learned you cannot trust them, and you have to apply a measurement method where you use the blade contour. Even though if the 0-degree mark look, well, this is not one, but if they look really proper, they are not always attached with a sufficient accuracy. So, and in other cases, they maybe look suspicious, like here, hard to read, hard to check, or maybe they are missing at all the proper plaque, and you're wondering which of these ones apply. So then at least you get a suspicion, and which helps that you check with a different method on it. And okay, we have also found some where there were no markings, but at least then you do something about it. So if you adjust the blades, you will be rewarded with an improvement of the power curve. And this one here is based on operating data of one turbine, where we measured the blade angle deviation that was about minus 0.7 degrees. That's about twice the critical limit value. So we took the power curves before the adjustment, the gray ones, we have two actually here, and then we looked at the power curve after the adjustment, so the green one. So we do see that we have an improvement here, and you see with this curve, it shows you the percentage of improvement, and we see that we have about 4 or 5 degrees improvement for higher wind speeds.
You have 2 more minutes.
Okay. This is kind of my last slide. This is a cost-benefit study we did. Our optimized balancing procedure here, this is for a wind farm with 10 wind turbines. If we measure all the blade angles at the beginning, at commissioning, and check the mass imbalance, it costs us 1,000 euros, and periodically check them later, 100,000 euros. So if we don't do it, these are cases where we don't do it at all, no measurements. We will have costs for damages due to mass imbalance, due to blade angle deviation, and also yield loss. And this is just with different assumptions for how big these will be, the losses. So we see this spans from 1 million to 7 million. But you see, even if it's just 1 million, it's kind of 10 times the amount of what the measurements cost you. So this is my conclusions. So unfortunately, only a minority of wind turbines have correctly adjusted blade angles. And the large share of faulty adjustments, they prove that the procedures in place so far for production and commissioning are not sufficient. And if you neglect that, you will have to deal with huge losses and with damage costs, and that can be avoided by a proper adjustment where procedures are in place, and that only costs you a fraction of what you will lose. So blade angle correction is an essential tool to boost the annual energy production and life expectancy and lower your operating costs.
Thank you. We have time for 2 questions. Yes, please. Introduce yourself. The microphone, please. Who is giving the microphone?
My name is Ozol from METÜ Center for Wind Energy in Middle East Technical University in Ankara. Now, my question is, you showed a power curve showing the effect of blade angle deviation towards feather and towards stall.
Yeah.
One of your first few slides.
Sorry.
Right. Yeah. So especially for when there's a misalignment towards stall.
Yeah.
It's really disturbing to see. It's a huge difference. Is this turbine dependent and geometry dependent, or is this some kind of average? Because if you have 1 degree misalignment towards stall, yes, it will stall easily when you go to higher wind speeds. But is this bad for all turbines?
This is a schematic. This is really schematic in order to show you the effect.
Okay, this is not the actual data.
No, it's not an actual. But we have seen that, but in order to show you the effects, that is schematic. But of course, it will depend on how big is the deviation. Mm-hmm. So, and we have really seen our turbines where we have really a huge loss in power. So they never reach actually their power output they are supposed to have. And we have had some turbines, I showed you some pictures later, where we saw broken blades on the ground. So this was a combination of mass imbalance and stall-induced vibrations, actually. Because if you have a stall earlier, maybe even different on the different blades, that you will really increase the loads. So,
And you do the measurements when the blades are stationary, not rotating?
yes, we do that where we adjust them, yes, in a certain position. And we do a calibration of the measurement as well. I didn't mention that. But
Okay.
yes.
Okay. Thank you.
Thank you very much. Thanks to Anke. Thanks.
Okay.
And now we go to our second speaker, Behzat Bigdeli. Behzat Bigdeli is the founder of Exponential Advisor, a consulting practice based in the United States, which focuses on utilizing its global network to develop technology centers to support R&D partnerships and assist in mergers and acquisitions of technology companies in EU, US, and Asia, China, India included. He has over 24 years of global engineering experience, working for the Boeing Company, United Technologies, Whirlpool Corporation, and Vestas Wind Systems after completing his Master of Science degree in Aerospace Engineering at the University of Texas. He has also been serving as the technical advisor to the board of directors of Sunny Group in China and Godrej Industries in India, in addition to consulting with Areva, General Electric, and many others, including financial institutions and various law firms. He will make a presentation on German wind R&D center development, Sunny's case. You have 20 minutes.
Thank you very much for the introduction, and I think I can skip that one. Basically, there is quite a bit of interest from particularly Chinese corporations in having access to technology and being able to gain from what is currently available in the Western world, whether US or Europe. One of the functions, as it was mentioned, that I perform is to try to help, thank you, sir, my clients in developing R&D centers in different countries that they have interest in. This is rather older case for the Sunny Group. This is already established. I have a current project near my hometown in Texas that is another Chinese company, Nanjing Gear Company, that they make gearboxes for many wind turbines. And their project is ongoing right now, and we're establishing that. The picture you see here is actually the completed center in Germany. This is near Bedburg. It's near Cologne. It's in Bedburg, actually. And I will try to explain a little bit of what we have gone through this process, the challenges that we have encountered as doing that, and also of what we learned from the project. So for those who are not familiar with the Chinese manufacturers, Sunny Group is world's largest, or in China, #1 in many ways in heavy equipment. They make construction machinery, they make mining equipment, excavators, and they have also recently made a number of acquisitions in Germany, including Putzmeister Group for concrete pumps and other areas. So they are significant, and they're #1 in the world in a number of areas, for example, excavators. So basically, the idea was that they did not, at the beginning, wanted to, and partially with their will and partially the situation in Germany and other European countries, US is no exception, by the way, a lot of opposition to acquisitions by Chinese, and as a result of that, they chose to establish the R&D center themselves and basically making the greenfield development. And then they chose the Bedburg site as it was, and then we went through the process of negotiations for all the tax benefits and everything else that is involved in that process, and finally going through the hiring process and trying to establish the center. And there was a great view from the Chinese that by establishing the center, they would be able to hire more R&D engineers, access the Western technology, and also be able to get funding and from the EU and other organizations, and sort of improve the cooperation that they have had in the past within China. So we had at different years that we went through these different goals for each one of the years. One was, of course, recruitment of the engineers. Another was accessing the technology, then establishing metrics for the organization so you can gauge the progress of the center, as is always the case with any engineering organization and otherwise. And then, of course, we wanted to be able to establish that center there. One of the center points of ideas that I tried to introduce to my Chinese bosses was the autonomy of the center, which I felt like it was an important factor, which is not very much part of the Chinese culture, but they sort of managed to agree to some sort of a negotiated way that the leadership, the local leadership there would have ability to do R&D without too much orders from China. And then, of course, establishing the roadmap was another part of it, that we wanted to make sure that everything would be in accordance with the highest Western standards that are available for this type of centers. We would want to have rotation of engineers, ability for Chinese engineers to come and work in Germany, and for the German hires to also go to China and become familiar with SANI and how they operated. There were naturally interests in working with German institutes and research centers, and also participate in conferences and so on, as is normal for this type of centers. And then initially the idea was that we will establish a core team of load engineers and controls, as all of you familiar with wind turbines know that those are the core disciplines, and so that was the initial goal, and then later on try to get into bidding for different R&D projects and implementing different approaches to the new turbines, which is something that a lot of manufacturers in Europe are currently implementing and doing, but for Chinese companies it's something new. Modularity in design, all the ideas, some of the Six Sigma practices and so on are things that are not very common, so we hope to introduce all of that as part of the establishment of the center. And then as we went through the process, the great learning experience was, of course, the fact that when you are a foreign company and coming to another country, aside from the existing oppositions to Chinese in almost every country, that sometimes even we have had before I go to Germany and discuss the challenges of Germany. Perhaps I should mention that similar issues exist in the United States. Their higher Chinese appliance manufacturer wanted to purchase one of the American brands, and US government actually encouraged Whirlpool company to come in and purchase Maytag to prevent Chinese from the acquisition. So Germany is no different, and there has been a lot of challenges and resistance from local government and from people and so on in establishing centers or having Chinese come and basically buy properties and so on. But aside from that, SANI, while it's very well recognized in heavy equipment industry in Asia, they're not really recognized in Europe. So that was one of the #1 challenges. And the anticipation was that, okay, the brand is not recognized, but you can still offer a lot of money and hire skilled engineers. But that didn't turn out to be the case because, again, in contrast to US, in Germany and Europe as a whole, really the way the system works, offering more money does not translate into actually a lot of interest. So that was not very successful. Another lesson was that choosing a center based on a location only for the purpose of tax incentives that they could get from the German government, like Bedburg, does not mean that that's also attractive to the candidates. A lot of wind engineers work in Hamburg around different centers that various of my clients as well, Areva, Mitsubishi, and so on, have centers there. And then it is certainly getting those engineers interested to move to Bedburg and is close to impossible. So hiring experienced engineers was also an issue with the center. Then there are a lot of bureaucratic challenges within Germany that those who are familiar, I mean, from very basic, opening a bank account is a nightmare. For a foreigner in Germany, you have to first get the work permit, then first the residence permit, then the work permit, then you're allowed to open a bank account, and then for Chinese to understand that, because in China anybody can walk into a bank and open a bank account, and it's no issue. But Germany, it has its own challenges. There are also a lot of issues regarding getting the visa. We had anticipated that once we go through the process for a center that Frau Merkel has been there as part of establishment of the center and the signing, getting a visa for an engineer after the first few would not be the same process and would improve process. That happened not to be the case. And we had to go through a very strenuous process for every engineer, foreign engineer that we would want to get permits for. And then there are also issues with the rotation. We wanted to rotate the engineers between China and Germany as part of the center. So the list goes on. I don't mean to bore you all to death, but for any company that decides to take on that kind of challenges, in particular if they consider establishing it in Germany, then they should really pay attention to a lot of this. And we have certainly documented a lot of this. Actually, German government has been involved with it as well. They invited me about a year and a half ago or so to Berlin, and as part of a Sino-German Innovation Forum, and I presented a laundry list of challenges. So some of them have improved. I'm glad to report that it has changed, but of course not everything. And this is basically a short summary of the conclusions that we have learned. I think cultural differences and mentalities cannot be overemphasized. Those are really important, especially when there is a huge difference in cultures between, for example, China and Germany. The others I have already mentioned: bureaucratic processes and recognition of the brand and recruitment issues, and also importance of the location. And perhaps number one on the list is having realistic expectations. I had established centers for my former employers, such as Whirlpool Corporation in Poland, next door to Germany, and also in Saarland, in Germany, and other areas. And I had never anticipated that trying to do the same thing for a Chinese company would be 10 times more difficult. So my expectations were not realistic, and it's always good to manage that as well as part of the process. Thank you all very much, and I'll be glad to answer any questions you might have.
Thank you very much. Now we have time for questions for him. Anybody else? No, please. Microphone is coming.
My first question is, could this have been done easier in the US?
Yes, as a matter of fact, SANI established a center in Atlanta, Georgia, simultaneously and in parallel with Germany, and I actually presented this to the German government. It was a parallel project, and the success in Atlanta was quite an achievement, much faster, much more, because US system pretty much is so that if you're bringing money, money is God. So you can pretty much do anything you want. There is not, as long as you're not violating any laws of man or nature, you're pretty much able to do what you want within your property. And it's not so many regulations, it's not so difficult to do some of these things. So definitely we have a living example that in parallel the project is started, and it was much easier to establish in the US than it was in Germany.
It's also related to wind turbine design, or?
No, I think that these challenges, in particular, well, the particular aspect that relates to wind turbine business is that wind industry is a very small industry relative to others I have worked in, for example, aerospace. So you have a very small pool of candidates to recruit from. If you're trying to recruit a few engineers, you're going to be recruiting either from Vestas or from, and you're in Europe or Germany, so the pool is very narrow. So therefore, it becomes very difficult in order to compete with those. And with location, with various things. Would you rather, as a German engineer, your employer be Vestas or Nordex or be an unknown Chinese company? Obviously, it's not as attractive. And because money doesn't translate, now in the US, you can get people to work in boondoggles. I know great engineers working in places that perhaps many people would not want to go around, but they pay 3 times what you would get in Dallas, for example, and people go. The motivation is there and you can do that. But we tried those in Germany. I actually had similar experience in Denmark, and same thing. When you offer overtime, they pay so much taxes that it becomes meaningless. The value-added tax in Germany now is 19%, correct me. We have none in the US. So when I offer my consulting services in Europe, it's always at 19-20% discount to my competitors, because I'm based in the US and I only pay US taxes, and there is no VAT. So right off the bat, I offer a 20% discount compared to the same guy in Europe that can do the same thing.
So the Bedburg Center is currently participating in EU projects, EU funding?
No, this was a brand new project funded by SANI, and there is no local funding for the center. Okay. This was all SANI's money, and basically, really, SANI Group is owned by one person, richest man in China, Mr. Liang. So there is some equity that is traded on Shanghai and Shenzhen markets, but that's about 30% of the outstanding shares. So about 70% of it is owned by one person. So it was all private Chinese money that came in, with the caveat that private in China does not exactly mean private in US, but nevertheless, yes, it was. No, there were no help. There were a lot of promises from the German government at the signing, as I mentioned. Mrs. Merkel were there, and Mr. Liang and all, and we were all there when the signing took place, and there are great promises of help in the process. And we thought that meant that the help would be with the bureaucratic process, because after all, the visa and banks and all these are operating under the umbrella of the government. But in practice, it means nothing. They can say all that they want. The bureaucrats are sitting and following their own rules, and it takes 3 months to get something done, and that's what it is. And multiply that by 100 times, going to take you a couple of years to staff that center.
Thank you. Thank you very much. Do we have any other question?
Maybe a remark?
Yes, we have a remark from Anke. Yes, please.
This?
Yes.
Yeah.
You are set.
Okay, yeah, I'm sorry to hear that. It was, okay, I'm German, probably the only German in the room here. So I'm really sorry to hear that it was so complicated. Well, I probably agree, it is very bureaucratic, but I'm a bit shocked that it is that democratic. And okay, I can understand the location problem. I don't know Bedburg. Maybe I just could say, okay, next time try Berlin. It's really, people really want to stay in Berlin, and we have lots of universities, lots of engineers, and also research going on. So, okay, for us, it's not hard to recruit there. So maybe if you try another attempt, I can recommend to come to Berlin.
Yeah, very good suggestion. But, you know, there are no tax incentives for a direct foreign investor in Berlin.
Okay,
so
that's...
In order, they, as every government does, in Turkey it's the same as well, they basically put the certain zones they define and certain areas that you can get particular tax benefits and support. And so you have to stay with those if you want to get those benefits, and that's usually what is touted before investors come in. And Berlin is one of them, and that's the issue. That's why I had put on the slides that you have to choose between your tax advantage or the success of your recruitment process. That's the choice you have to make. So.
Okay, thank you very much. If there are no more questions, thank you. Thank you very much. Now we have our third speakers, Didier de la Una, correct?
Correct.
Okay. And he is, since 2002, founder and CEO of Meteodyne. Metodyne develops innovative services and software for wind resource assessment, wind and solar forecast, wind safety in the field of energy, transportation, building and construction. Between 1990 and 2002, he was the head of computational wind engineering department of French Scientific Center for Building Industry. In 1983 to 1990, wind energy engineer at CSTB. 1981-1983, researcher, and he had his PhD in atmospheric sciences from Paris 7 University. Is that correct? The number of the university is Paris 7. Okay, I didn't know that. Thank you. The floor is yours, and he's going to tell us about considering thermal stratification in CFD modeling for wind resource assessment.
Thank you, Mr. Chairman.
Do you have 20 minutes, ma'am?
It's okay. So I'm going to speak about scientific thing, which is thermal stratifications in CFD modeling. First, a rapid presentation of Metodyne. So since 12 years, Metodyne has developed a software which is called Metodyne WT, which is a CFD software and which is used for wind resource assessment in complex terrain in particular. And so we have offices in China, 2 offices in China, one more than offices, affiliate companies, one in India, one in Philadelphia in USA, and we have a lot of distributors, and in Turkey our distributor is UCL Energy. And UCL Energy can perform support and demonstration and give you a lot of information about the software. So we develop also other software for wind, for instance UrbaWind, which is a computation of wind around buildings inside cities, and Metodyne forecast to estimate the forecast for wind production for wind farms. And now we are developing new tools for solar forecast and also solar resource assessment. So my presentation about stability, firstly we will give some definitions about stability. Secondly, I will describe the current turbulence model which is actually implemented in Metodyne WT. I will try to explain you why we need a new development in stability modeling, and then I will show you the extended Metodyne stability model and calibrations on 2 sites in Cabao in Netherlands and Rodersberg in Deutschland with measurements at up to 200 meters height. And then I will do a conclusion. Some definitions. So the thermal stability generally is defined either by what we call a Monin-Obuchov length or gradient Richardson number. So the Obuchov lengths give the ratio between the heat flux and the momentum flux. So more important is the dynamic, which is represented by the momentum flux. Higher is the value of the Obuchov length. These values of the fluxes are difficult to measure generally, and especially in the wind energy industry. So generally we know the gradients of temperature or gradients of wind. So there is another number which is called the gradient Richardson number, which represents the same things, but which is the inverse, in fact, of the Obuchov length, and which gives the ratio between the fluxes, but deduced from the gradients, which is much more easier to calculate, to measure. So there is a theory which is called the Monin-Obuchov similarity theory, which allows to link the two variables, the Obuchov length and the Richardson number. The question is the Monin-Obuchov theory valid, and where is it valid? So in WT, there are, we solve, of course, the Reynolds Navier-Stokes average equations, and we have also to make a modeling of the turbulence. So the turbulence, it is the flux. You see, in the equation, we have the flux of momentum, and we make the hypothesis, as in all the CFD software, that these fluxes are proportional to the gradient of the mean values. So the model consists in estimating the value of the turbulent viscosity. So in WT, this value is expressed as a product of the square of the turbulent kinetic energy and the turbulent length scale. Then the turbulent length scale is deduced from an equation of transport, a classical one, and the turbulent length scale is deduced from empirical results that are fitted to the atmospheric boundary layer. It has been described since a long time. And in this way, we have a better representation that, for instance, in a K-epsilon model, where the epsilon equation is not adapted to the atmospheric flow. So how do we handle the stability in this model? In fact, we just have to reduce the turbulent length scale as a function of the stability. For instance, there are some stability classes in WT. When you are in the stability 7, the turbulent length scale are reduced from 33% from the neutral stability. And then in the model, for instance, when you are in near neutral, the Abakoff length is very large, of course. But when you become more stable, class 4, 5, 6, 7, we reduce the length of the turbulence length scale, and the model that we use, the Monnin-Abakoff length is also reduced in the same way. And at the beginning, the model has been calibrated on flat terrain and classical theory. And here you see measurements are not measurements. The theoretical model of the Monnin-Abakoff theory are the crosses, and the lines are the model. We say that for moderate stable classes, we have good fitting, but we see that if the stability becomes higher, for instance, in stability class number 5, when we are at higher altitude, higher heights, we say that there is a difference between the theory and what we obtain from Meteodyne. But you can notice here we are at 200 meters. Up to now, it was not very important because nobody cared about values of the wind at 200 meters. But now, wind turbines are much higher, and and especially for the offshore winds. So now we are interested in these parts. And in this part, the stability defined by the Richardson number is very high, and we are sure that the theory is no more valid. So up to now in Meteodyne, we use the notion of effective average stability. You know, for a given wind direction, a CFD calculation is performed with an hypothesis about stability class. So we suppose that for this direction, the stability class is always the same. So in fact, it can be allowed in a statistical approach. In fact, the stability class that we choose in Meteodyne WT will be the class which will fit the best for the results of the model. But the problem is that, in fact, we are not sure that the extrapolation of the wind distribution is correct. We know that the extrapolation of the mean wind speed is correct because the stability class has been defined in this aim, but we don't know exactly what happened for the full wind distribution. So the solution, and now more and more people work like that, is, for instance, to work with time series. This time series, you must know at each time step what is the stability. The problem is that doing like that, you have to deal with more stable classes because it is no more average stability, but stability at what moment. For instance, we have a distribution of stability classes in Cabao. I will show you later the site. And another example in Rodeserberg in Germany. And you see, for instance, that we have a lot of classes, stability classes at 8 or 9, which is very, very stable. When we consider, sorry. Yes, when we consider the energy, stability, the distribution of energy, stability, high stable stability, are less important because the wind is lower in these cases. But it can concern about 10% of the cases. So the objective of new developments is both to handle strong stability cases for the time series approach, and secondly, to be able to extrapolate to higher levels, because at higher levels, the stability class is higher. So we have chosen to use a model defined by Zilitkevich, for instance, or Grachev, which consider multi-layer models. It means that the stability of the atmosphere cannot be considered as a single stability class, but we have to consider really what happens at different levels. So we calibrate this model on a flat terrain, and then we validate it on a complex terrain. So you see here the different layers we define. So we have the constant flux layer close to the ground, where the dynamical process are the most important, and the thermal can be neglected. After, you have the classical Monino-Bukov stability theory layer, where the turbulent length scale is constant, like in the classical theory. But we define above a local Moss theory where the turbulent length scale can vary. And then we have the free layer, which in fact is not really a free layer, but which is a layer defined by the mesoscale situation above. In the model parameters, so we have Bukov length, we have the 8 of the Moss layer, the 8 of the local Moss layer. We have defined also a minimum length scale for the turbulence, and we have also to define the situation of the thermal stability in the free layer. So a lot of parameters.
You have 4 minutes.
Sorry?
4 minutes.
So you see here the terrain where we have calibrated the model. So it is a very flat terrain and a tower of 200 meters. And then we have classified the stability, the data according to the stability. And you have here the frequency. What is interesting to note, here you have the ratio between For instance, this line, it is a ratio between the wind speed at 200 meters and the wind speed at 40 meters. You see that when the stability is increasing, this ratio is increasing as it is expected in the theory, in the Money-Nabokov theory. But we see that when the stability is higher, we see that this ratio is decreasing. So it is very surprising. In fact, the reason is that the higher level, so here at 200 meters, from this part becomes above the stable layer. So it shows that we are obliged to consider this case. And we see the same thing if we consider the ratio between 440 meters. We see that the ratio reduces after class 8, for instance. So it means that in this case, the 8 of the stability layer is about 140 meters. And the same here, the 8 is about 80 meters. So the calibration of the model, we see that here it is near neutral. So the profile here is more and more stable. So the points are the measurements and the model, so the calculation by WT are in the line. And after, if we go to more stable cases, we see that the profiles go in this direction, less and less slope, less and less gradient. Here we are in the more stable case, and it is measurements. And our model is able to reproduce that in this case. So the same for the turbulence profile. So I have not a lot of time, but I just point out the error is about here maximum 20% for stable case for the turbulent kinetic energy, which is correct. Model parameters. And then the validation of the model. So we consider a forested and hilly site in Germany with 200 meters height mast and measurements during 1 year. And also flux measurements with sonic anemometer so that we can compute the Money-Nabokov length. And then we validate the model. So for different turbulent Money-Nabokov lengths, we see here that the point in black is for Money-Nabokov lengths greater than 100 meters, and this one is only between about 40 meters in average. We see that we reproduce well the profile, and we see also that the effect of stability is not much less evident than in the flat terrain. But the model has been able to reproduce that effect. And here you have the turbulence intensity deduced from the model and from the experiment. So another case for east winds, also in Rodezerberg. And we see the same phenomena. You see that when the Money-Nabokov length goes to about 200 meters to 40 meters, the wind profile does not move a lot, less than in a flat terrain. So we don't know exactly if it is due to the forest or due to the hilly terrain. So this analysis is linked also to the modeling of the forest. So we are also working on it. But in any way, we have this effect. For the turbulence, we see that there is no difference in the measurements for stable cases and strongly stable cases. The model will give lower turbulence, but the error is not so much. Okay, so the conclusion. So the present stability model inside the Meteodyne WT has been validated up to stability class 7, which is a moderate stable class. Classes 0 to 7 is useful in WT when you make a statistical approach, when you use the notion of effective average stability. When you have a time series approach, you are obliged to consider stronger stabilities. So a new model has been elaborated. This new model has been calibrated on Cabao data and validated on a complex terrain, Rödezerberg. So we are continuing research. Of course, it is not finished, but the objective is to implement this new stability model in WT 5.3 at the end of the year. Thank you for your attention.
Thank you very much. Thanks. Now we have some time for the questions. For him first. Ozbey.
My understanding is now that you're using basically a one equation turbulence model in which you have a differential equation for K, and for the Molyneux-Nabokov length are you calculating the Molyneux-Nabokov length and tuning it later with the measurement data? Is this how it works? Is this how you do it?
Excuse me, you are working,
for your turbulence model, you have basically a one equation model.
Yes, yes.
So you're solving the K equation, and for the Molyneux-Nabokov length, you are solving it locally with some algebraic equations, and then you tune it basically with the experimental data. Is this how it works? Does this how it works out?
In fact, the experimental data are for the wind speed and for the temperature. There is, when we validate, when we calibrate on Cabao, we don't have a turbulent length scale measured. So the turbulent length scale that we define in the model is a turbulent length scale that fits, and not only the turbulent length scale, also the height of the different layers, which fit at best the results of the model. And after, there is a link to make between, for instance, the Molyneux-Nabokov length, which is measured in Rödezerberg, and the values that we put in the model. So at least for the most layer. And so at the moment there is a difference. So maybe there is a ratio of 2 between the two turbulent length scale.
Right.
So we have to understand why.
In your Germany measurements, you had pretty much flat turbulent kinetic energy data.
Yes.
But that was not the case for your model. So
yes, it was relatively flat, more than expected for stable cases. And we see it both in the model and both in the experiments. And the reason is that the wind profile is very different because there is acceleration due to the hill, there is forest effects, and so on. But okay, the model is able to reproduce this, all these effects together and to give the...
Okay, thank you.
Thank you. Any other question? Any comments from, why don't you take your seat over here? It's okay. They don't have any question. You can come. Okay. Thank you. Now, if you have any comments, please go on. We have some more time, 2 minutes each, if you want to add anything. Yes?
I have some questions.
Yes, please.
I have a question for Anke, and it's not related to Berlin. I'm curious about the cost of this procedure. You mentioned that in one day, you guys could go out there and do this measurement. Now, we all know that this will have to be, in practice, and theory is all great, but for example, my client in Inner Mongolia that gets the blade damaged on a bi-weekly basis, how often do you think that we should repeat this process, and what the cost would be in that? I mean, does your company offer a per item cost, or is it a fee that they pay and then periodically you guys check the angle?
Okay, we offer, it depends. We can offer something per turbine, but then we have to be sure how long it takes on site. So we very much depend also on the technical support on site, really to operate the wind turbine, to place the rotor. And so we usually are charged per day. So just,
okay.
But it's not, if you would say just the blade angle check, I would say if it's not in Mongolia and we have to go there, so that would be travel costs would be very high. But you should have that for less than 2,000 euros. So it's not that expensive.
For the
for one measurement of a blade angle, for instance.
Okay.
And it just
And how frequently do you propose that to be done? Usually for your sites in Germany.
We really recommend to check that in the beginning. It can be an easy check if there's something wrong or not. Then you could also go to the manufacturer and claim that there's something not correctly adjusted, and or before end of warranty. But otherwise, we maybe sometimes it also depends on the type of turbine. But we would in that strategy I showed, we were checking or would recommend to check every 3 years with a simple check. So. But this is mostly to check on mass imbalance, because that will change over time. Usually the blade angle adjustment doesn't change, but for instance, if you have a hydraulic pitch, so it will change slightly, and if you have maybe some adjustments or made in the control and how the wind turbine is run, you can also have then influence on the blade angle setting. So, but mostly, what I said, that's what we recommend. And of course, if you have any incident that, for instance, you have a damage to the blade, or you repair something that is more in regards of mass imbalance, of course, then you should check.
For the mass imbalance, okay, very good.
Thank you very much. Thank you very much, all. This session ends now. I think we need to give the certificates. You like to come also? Yeah? Yes, please. Okay, thank you. Thank you. With my pleasure.
Thank you very much.
Take the